Okay. Hi, everyone. Welcome to one of the last silo seminars of the semester. We still have one more next week, right? It is a pleasure to have Ben Grimmer visiting us and giving a talk today. Ben is an assistant professor at Johns Hopkins University. He works in optimization. I have known Ben since he was a grad student. I knew him for his work on non-smooth optimization algorithms. Since he started faculty position, he has been focusing more on computer-assisted approach to optimization and optimizing optimization methods, which is what he'll talk about today. He has been a very successful optimization researcher doing really strong work. As you can see, he's a Sloan Fellow, and so he gives great talks. So it's really great to have him today. And please take it away.
Thank you very much.
I'm just curious, which department are you in?
I'm in applied math and statistics.
Okay.
But we've had name changes over the last couple decades.
Yeah.
So at one point it was OR, at one point it was mathematical science.
Yeah.
So if you liked people in those departments, I'm like them.
Okay.
Otherwise, I'm in a totally new. But thank you all. Thank you for the very, very kind introduction. So I'm going to tell you some today about optimizing optimization methods. This has been a kind of direction I've gotten rather obsessed with the last few years. But this work that I'm going to present was all done with two phenomenal collaborators, Kevin Shu, who is currently a postdoc at Caltech. I think he's going to be doing this coming job market. So if you like what I have to say, you should bring him back and he'll tell you even cooler things. And then Alex Wong, my other collaborator, is an assistant professor at Purdue. Nothing I say today would have happened without them. So remember their faces. Okay, the big picture of what I'm going to talk about, I want to take the first bit of time just to get us up to the same kind of present day standard of what's known about minimax optimal optimization methods. So these are the methods that perform the best that we can guarantee against some class of problems. That'll give us this idea of minimax optimality. And there's been a tremendous amount of great work building up to that point for about 50 years. And then I'm going to make two advances on this, trying to move the state of the art forward in two particular ways. This thing I'll call subgame perfect methods, and then a totally different direction, which is trying to get an optimal version of gradient descent. Those kind of two orthogonal thrusts that use the same toolbox and the same ideas. I gave this talk at Purdue last week, and I had a ton of questions about the first part and barely got to the second part. I would love to do that again. So please interrupt me with questions so I can be maximally clear and convincing as we go through. I'll be happy if I never make it to the third part, but you all understand part two. Okay, so we're going to be thinking about optimization problems, minimizing some function f of x. And we're going to take maybe the most standard setting. So I don't want to deal with unnecessary complexities. So I want to say that the function we're minimizing is L smooth, meaning that it's differentiable and the gradient doesn't change too fast, changes at most at rate L. So that smoothness number L in my picture here would say at these places where we change quickest, L is bounding how quickly the function changes when it curves most quickly. I want F to be convex. So there's actually a global minimum that we're going to make our way to as we follow gradient directions down. And it has some minimizer. So we won't be running off to infinity or something like that. That's the type of problem I want to look at. The type of algorithm I want to look at are these gradient span methods. So at every iteration, the method will compute a gradient at the current iterate and come up with a next iterate based on some combination of all the past gradients. That's a really general definition, but that's the type of algorithm I want to think about. And really, I want to think about problems and algorithms as the core objects. When I'm doing design, I'm wanting fast algorithms and I'm wanting to understand hard problems. So those two things are in opposition to each other, and they make the foundation for understanding what's happening. So when we fix where we're going to start our method, we fix that we're going to do n steps of an algorithm, and L is the smoothness. Given all of those is static and agreed on ahead of time, we're going to run 20 steps of a method from some start point. We could ask for the a priori worst case of a given algorithm. If you propose your favorite algorithm, I can ask what is the worst performance, meaning look at all allowable functions f. Allowable means satisfies the stuff on the previous slide. What's the worst performance? And I'm going to measure performance in this talk by the final objective gap, how different you are from the minimizer. But I want to put it in relative scale, because of course, if you just put the minimizer really far away, you could make this gap as big as you like. So relatively, I want a small objective gap, meaning this objective gap normalized by the Lipschitz constant L and the distance to optimal squared. That ends up being the right normalization. But figuring out what's the worst case is figuring out what's the worst this performance ratio can be over any smooth convex problem. Dually, and I really mean that dually, you can take the a priori worst case of an algorithm and say, over all allowable algorithms, everything meeting my gradient span condition, what's the best an algorithm could ever do on my given problem instance? So a hard problem would be one that no gradient method could get a small performance ratio on. Those two things are in opposition. Really, when I'm doing algorithm design, I'm wanting to solve a min-max problem. The best algorithm would be among all allowable algorithms, which one gets the smallest worst case performance on any allowable problem.
The previous slide, when you said span of those previous gradients, at some point it becomes just the old RD. So
right. So
are you allowing them to be anything? So xn could be anything after the iteration. Then.
Yes.
If the gradients are.
Yeah. So this algorithm model, once you found a set of gradients that span the whole space, then I'm allowing the algorithm to do anything. So really, this captures a stupid number of algorithms. Like there are algorithms in this class that are, of course, entirely impractical because once I've seen all the gradients, you could say my algorithm goes to the minimizer. I have no idea how to implement that, but it would meet the requirement. So when I say minimize over all allowable xn, that includes these ridiculous algorithms that have found the whole span and then jumped to the minimizer. So prior to finding the whole span, we have an interesting thing to figure out. Okay, so algorithms and problem instances give us these two competing things that we would like to find the best algorithm against the worst problem in terms of this performance measure. There's been lots of study in the past about how to do this well. If you took gradient descent as your algorithm, the kind of canonical step size is 1 over the smoothness. Your algorithm could just iterate, take the previous point, move in the negative gradient direction a particular amount, and repeat. And if you do that, you can guarantee the performance ratio. The worst performance over all smooth convex functions shrinks at rate 1 over 2n plus 1. So we have a guarantee. If you run that algorithm, you can get at least that good of worst case performance. And as you run longer, your guarantee gets better. Recently, some work that I think Jason Altshuler came here and gave a talk a few weeks ago, maybe a month ago. Jason's results with Pablo Carrillo said if you choose some magic silver step sizes that I'll talk more about in part 3 of this talk, you can get this performance ratio to shrink like 1 over n to the 1.27. So you can get it to shrink faster. That's better. If you don't limit yourself to gradient descent, Nesterov famously gave an accelerated method. If you do this thing with momentum, you can get the worst case to shrink at a rate that looks like 4 over n squared. So we're getting quite a bit faster. And okay, Drury and Tabul and then Kim and Fessler came up with this optimized gradient method that somehow really pushes the limit. And if you really optimize your algorithm, you can get your worst case performance to look like 1 over tau, where tau n is this recursively defined sequence. I don't have a closed form for it, but it behaves a lot like n squared over 2. So asymptotically, it's a factor of 2 better than Nesterov. And okay, a factor of 2 is not so interesting on its own, but this tau number ends up being really important. So if we go about building lower bounds, taking the dual perspective, we've known. In particular, Nesterov gave a nice quadratic function that no gradient span method can get a rate faster than 2 over 2n plus 1 squared. So you can't do better than rate 1 over n squared, big O. Drury in particular gave the best possible lower bound. He said that I have an instance that's piecewise quadratic, and no allowable algorithm could do better than 1 over this tau number. And that tau is the same tau as the previous slide. So we have this optimized algorithm. We have a very optimized worst case. No other algorithm can do better than that optimized gradient method because of this lower bound. So we've kind of pushed from both ends and found exactly the middle point. Okay, there's lots of other works that I don't have time to tell you all about that handle all the more interesting settings out in the world.
Just a quick question. Maybe
Yeah.
get into it. So you
Yeah.
can tell me what they are. But I mean, are all these like this optimized gradient method? Are these all
Yeah.
like what? Do they need extra information, or they're totally realizable?
So the optimized method is going to need these 3 things. In particular, the 2 that are really assumptions. It's saying how long to run and what the smoothness is. And there's all sorts of workarounds to not have to know n and l. But the methods need those, and then they need access to gradients, but that's it.
And if I just have a upper bound on L, is that okay?
Your final guarantee will then be off by your upper bound. So you won't get exactly the perfect guarantee. Your upper bound would show up.
Yeah.
So in my language, it wouldn't be minimax optimal. You're now going to depend on a thing that's not the ideal thing. But you could run the theory for sure with upper bounds. Okay, so you can do lots more with this. You could just restrict to gradient descent, and there's been lots of work pushing its theory. You could look at problems that have constraints or proximal terms that give you some kind of regularity and run with theory on those. There's all sorts of other settings where you want to minimize the gradient norm of your algorithm or do some kind of adaptive line searching to not need to know that number L. You can add strong convexity, and there's so many things you can add, and I'm not going to talk about those in this talk. So I would love to point people to that literature and give you particular references. These are super non-exhaustive, but that's not our focus. So in terms of the smooth convex setting, what we knew last century was that if you wanted this minimax optimal thing, it was on the order 1 over n squared. Nesterov got us 1 over n squared, and lots of people made lower bounds. Nesterov is who I cited, that said you can't do better than that. Then we knew last decade that the actual minimax thing is equal to this 1 over tau number. Those are exactly the best method, no big O's, no constants. Okay, so we know OGM is the a priori best minimax optimal method. If you don't know anything about what you're going to run on, you should run OGM and you'll have the best worst case. I'd like to, in this talk, move this story forward in 2 distinct ways. So I pointed at these earlier. I want to go beyond minimax optimality and give you a type of algorithm that meets a higher standard than just being the best in the worst case. And I'd like to tell you the best way to run gradient descent. But that'll move forward this kind of progression in 2 orthogonal fashions. So to think about how to do better than this minimax optimal method, we need to take a bigger lens at what optimization is doing. Because minimax optimal is really compelling. Like, that's a reasonable place you could have stopped developing theory, but I want to do better than that method. So I need to think about optimization as a game. When we go to solve an optimization problem, our algorithm, here I name it Alice, is going to repeatedly be picking iterates. Alice chooses what iterates to give next, satisfying this gradient span condition. And Bob is our bad instance builder. He's wanting to give us a hard problem. After we say, this is my next iterate, Bob says, well, here's the function value and gradient there. Bob doesn't necessarily have a function in mind. He just has to tell you a function value and gradient when you propose an iterate. And the only limits on Bob is that there must exist some smooth convex function that agrees with all the answers he's given. Bob can change his mind and be thinking about different functions at different times, so long as the answers he gave were always coherent of being interpolable. There should always exist a function so that if you called Bob out and said, hey, what smooth convex problem were we actually minimizing, he could tell you there is a function. But he's free to give any answers he wants other than that. We do that in a loop for a while, after our game is played and end steps are done, Bob reveals where the true minimizer was, some x star with some value f star and some 0 gradient, and Bob pays Alice 1 over the performance ratio. So Alice would like to get paid a lot. She would like a very small performance ratio. Bob would like to not pay out much. But that's what optimization is for my perspective here. When we want a good algorithm, we want to play this game well. And so just to be super concrete, I want to walk through the game with 3 steps. We agreed x naught is given. So in the first step, Alice has no span. So Alice has to pick the first step as just x naught. And then Bob reveals a function value and gradient there. And then Alice gets to pick x1 as something from that span. So Alice might pick that as x1. And Bob reveals a function value and gradient. Alice picks x2. Bob reveals a function value and gradient. Alice picks x3. And then Bob needs to reveal the function value and gradient there and tell us where the minimum is so we can pay out the game. And okay, so then we finish the game. Bob is given those answers and we can compute the payout. We can say how far was the actual minimizer from the initialization and what was the final objective gap. So that's the game of minimization. And developing algorithms is telling Alice what to do so that we play this game well. So we have a Nash equilibrium for this game. The history I gave you tells you, in some sense, how you should play this. If Alice said, I'm going to follow OGM, she can declare her strategy up front and say, at every step, I'm going to do the optimized momentum gradient method. Bob could declare up front, I'm going to take the hard instance that Drury made and published in the literature and just answer every question about that instance. Just always tell you its function value and gradient wherever you ask. If Alice and Bob follow those strategies, neither has any incentive to deviate. The 2 theorems I stated before said that any way Bob changes, Alice will always get paid at least 1 over tau. Any way Bob deviates would allow Alice to do better. Okay. The 2 of them are in Nash equilibrium if they follow those strategies. Yeah.
So that last step when Bob chooses those are also consistent.
Also bound by this.
Yeah.
I didn't write my orange note, but absolutely, when you say where the minimizer is, it has to be that there is a legit function that we could have been playing this game on.
Yeah.
Absolutely.
Okay.
Yeah, I couldn't just like put this point way down here. Yeah.
And do you allow randomization?
So as stated here, I'm not putting any limits on what the players do besides, well, okay, I'm not going to go all the way back. The algorithm here could be anything that satisfies this gradient span condition. So you can't randomly move in a different direction that's not part of that gradient span. But as long as you satisfy that condition, I'm happy with it. So Alice could do a randomized strategy and move either length 1 or 2 in the gradient direction, but you can't move in a Gaussian random direction.
Sure, but that's,
yeah.
The choice of the actual coefficient could be randomized. And
right.
Also same for Bob.
Same with Bob. Right. They could be giving random answers. We have a Nash equilibrium for the game. It happens to be a deterministic Nash. Okay, so we have this game and we have a Nash equilibrium. And if we think about game theory, we can decide that a Nash equilibrium isn't actually the end of understanding a game. That tells us a stable strategy. But if my opponent makes mistakes, a Nash equilibrium doesn't tell me how to take advantage of my opponent's mistakes. We can say that in a really simple example. So I want to run this OGM method. The definition of the algorithm is not so important. I put it here. If you've seen momentum methods, this should smell familiar. You initialize some initial guarantee tau and some auxiliary sequence z. And each iteration, you compute your current function value and gradient. And then you make some magic momentum choices. And then you update your variable based on a combination of a gradient descent step and your auxiliary sequence, and you update your auxiliary sequence. If you've seen Nesterov momentum, this superficially looks similar. The choices here are all different. They're optimized to get us that extra factor of 2, but it should feel like a momentum method. There's no other secrecy going on. And we've determined this a priori. Right? This algorithm is defined for any problem instance. It tells Alice what to do at every iteration of the game. If we run this on a really simple function, half of x squared, this algorithm will oscillate back and forward, and it ends up converging exactly at rate 1 over tau which is that worst case rate. So that's to say that if Bob was really naive, if Bob just answered as if the problem was half x squared, Alice would not take advantage at all. Alice would be very cautious and bounce back and forth and attain the worst possible rate because we didn't do anything to make Alice perform better in easy cases. We just wanted to get the best worst case. Okay, so this Nash equilibrium is not actually the best software for optimization. I wouldn't tell you should run OGM on every problem you encounter in life. In particular, this problem, what a good algorithm would do, I claim, is solve it exactly in 2 steps. If we had a really smart algorithm, if I was Alice and I'm playing as intelligently as I can, after I see a gradient at x1 and a gradient at x2, you can make the hard mathematical deduction that any smooth convex function with those 2 gradients actually has to minimize at the origin. So you should just go to the origin and say, I know this is the minimizer. Bob gave away the game when he told me those 2 gradients. I know where the minimum is. Report it. So a smart algorithm should see that and take advantage when Bob makes mistakes and gave you information like that. That's what I want from practical software. OGM doesn't do that. So my goal is to optimally take advantage of everything that Bob does. I want an algorithm that makes the best possible choices given what Bob has told me. I can articulate that as a certain min-max problem. What I want Alice to do is when we played up to around little n of the game, I would like that the way Alice finishes out the game to be minimax optimal. I would like that Alice will eventually produce a fine literate xn that had to come from some algorithm that agrees with the past that's already happened. We've already played the game up to around little n, so my algorithm has to agree with everything that's happened. And I'd like this algorithm to finish out the game to do as well as possible on any problem instance Bob could be thinking about, which would be any smooth convex problem, but Bob's hands are tied. He's already told me some function values and gradients. So Bob can now only be thinking about smooth convex functions that agree with what he has said so far. So if Bob gave bad answers like x squared, then his hands will be tied and he won't have much room to do mean things to me in this max. So I'd like an algorithm that not only is best at the start, but as I learn function values and gradients, is as good as possible at every remaining game, every subgame. In game theory terms, this would be a subgame perfect Nash equilibrium. So it's saying in any state we get to, we have the optimal way to finish out playing. So my technique for attaining this, I'm going to give you an algorithm that meets this higher standard. The approach is going to be to just generalize the OGM method. In particular, that algorithm has a really, really nice proof that took a while to get to, that came from Adrian Taylor and Francis Buck, giving a potential style proof that tells you what's being inductively maintained as you run that classic method. There's a nice monograph as well as this Park review paper that go into more detail on the particulars of the method that I'll be waxing over today. So when you run this optimized gradient method, what's happening under the hood is it's inductively maintaining a certain hypothesis. At iteration n-1, the method ensures that this quantity is non-negative for any possible function that we're looking at. So this looks like tau times almost the negative objective gap. Right, this thing looks like optimal value minus the current function value modified by the gradient. Plus a distance to optimal minus some extra term. But if you rearrange that thing being non-negative, you get that this is saying something like our performance ratio. Objective gap over distance to optimal is at most 1 over tau. So the OGM method inductively maintains that being non-negative, which is really inductively maintaining a certain performance ratio. There's a little twist on the algorithm to deal with these gradient squared terms that I'm going to wax over. But the algorithm just needs to inductively maintain that h, and we'd like to maintain it growing tau as much as possible. The bigger tau is, the better our guarantee is. So when I make my algorithm update from one iteration to the next, I want to keep this thing non-negative and grow tau a lot. That'd be a good algorithm design.
Just a question.
Yeah.
Potential. So is it true that any function that Bob or whoever could be thinking of has to keep that non-negative. Is that what you're saying?
Right. So Alice should have done their iterations so that that is non-negative.
And that, is that in any way like the sharpest characterization of this space of possible?
Right. So, yeah. So, where you get this kind of potential, if afterwards we've kind of done our analysis, we found our best method, our worst case instance, what should be the case and what is the case is if you go look at this potential on the worst case instance, all the H's are equal to 0.
Yeah. Okay.
So yeah, this in the worst case works out exactly totally tight,
Gotcha.
which gives us some clue that this was the right thing to be thinking about that we can check in hindsight.
Good, thanks.
So the OGM method, if you wanted to reinvent that induction I had before, what you would do is just stare at this hypothesis H. I know the current hypothesis is non-negative. I'd like to build the next hypothesis, Hn, to look like the current thing that's non-negative plus some coefficient times this inequality is something that's non-negative for every smooth convex function called co-coercivity, plus some non-negative number times another thing that is non-negative for every smooth convex function. So these two things are just smooth, or just non-negative due to smoothness and convexity. I won't prove why, but you can go pull up your favorite optimization textbook, and it will somewhere say those being non-negative is implied by smoothness and convexity. I'd like to build my next hypothesis as a combination like this that grows tau as much as possible. So you could just articulate, find me the best choice of my next iterates, the best choice of these coefficients phi and psi, so that I grow tau as much as possible. If you do that, you'll rediscover OGM. You'll find some choice for how these should come out. It comes down to some momentum magic, but it just falls out of saying I want that induction to go as well as possible. Okay, so that's where OGM comes from. To get a subgame perfect method, I just want to do this even harder. I want to say, if I know the function values and gradients that I've seen, I should be able to get an even better inductive improvement. Maybe I can grow tau much, much more. So if I have this history, I've seen the game play up to little n, then, okay, what we should do, look at m here to be the best iteration we've seen. Because if I'm looking at any subgame, I don't actually know that the most recent iterate's the best one. So, okay, minor nuance that any subgame, your best iterate might not be the most recent one. You need this number n to be your best iterate. But then you should choose your next iteration xn, your next value tau, this momentum sequence z, and a bunch of parameters to be the ones that let you grow tau as much as possible. So I want the biggest value of tau so that the next inductive hypothesis is non-negative. I'm going to make it be non-negative by taking some combination of the old hypotheses, some combination of these q star i's that are those inequalities on the previous slide between the optimal and the ith iterate that I said were non-negative by definition, some combination of the next iterate's relation to optimal and the nth iterate relationship to n. But those things are all non-negative by definition, and I just like the best inductive proof. So find me the best value of tau. That seems a little bit harder. Now we have lots of variables in play, and this problem is scaling as I run longer. Turns out this is not so bad. So if you go about that problem and tinker with it, you'll find it's an easy optimization problem. Finding the very best selection of these corresponds to maximizing a linear function in the coefficients mu and lambda, subject to one quadratic constraint and non-negativity. So I don't have a closed form solution for that, but it's about as easy as a not closed form optimization problem can be. Yeah.
So there was this lesser known Nesterov acceleration method, and the original version actually also had the search over two parameters. So he would two vectors.
No. So, okay.
So the search for the step size just boiled down to the space search symbol.
Gotcha. Yeah.
Things, right. So the same complexity for figuring out the step. Have you tried comparing to that?
I haven't. I really should. That's a great pointer. So I'll follow back up, and you'll get an email from me tomorrow saying it's the same or it's different.
I even have the source notes.
Yeah. Perfect. Please send me those. Yeah, so here we're not so lucky that it's 2D. There's a whole vector U of how we should use the past hypotheses. and a whole vector lambda star for how to use these relations to optimal. But you could just solve this problem, and you'll be told the very best way to move this induction forward, aware of all the past plays that Bob has made.
Yeah, could you say a little bit more
Yeah.
about the best way to move this induction forward?
Right.
Somehow I want that to be the most constraining new HN. Is that
Right. So really the thing I care about is this number tau. So,
Yeah.
right, because at the end of the day, I'm going to rewrite.
Yeah.
So at the end of the day, I'm going to rewrite the hypothesis,
Yeah.
and my rate is
Yeah.
1 over tau.
Okay.
So just tau is the one thing I care about.
Yeah.
I just want to get the inductive proof to work with the biggest value of tau, and we'll get the best guarantee. Well, this is just a greedy argument so far. You shouldn't be convinced this attains some greater standard.
Right.
I'm just saying greedily
Once-
push the induction as fast as you can from step to step, and it'll end up being the right thing to do globally. Okay, so as an algorithm, just to write it out in gory detail, we have our givens, define the initial tau and auxiliary sequence. Those are set up so that the first hypothesis is non-negative. And then at each iteration, figure out your function value and gradient, solve this planning problem that tells you the best way to push the induction forward. And then if the planning problem is unbounded, that corresponds to this kind of case where we exactly know where the minimum is. This problem will be unbounded exactly if a gradient step from your best iterate totally solves the problem. Otherwise, there will exist a solution, and you can just pull out your next iteration from that solution, mu and lambda, as just a static formula. So it's a little computationally more intense. I'm asking you to solve a non-trivial problem. And in particular, this problem needs you to remember your old gradients. So the problem grows in scale as we run longer. You can do a version of this method where you just remember the last 10 gradients, and you'd get a pretty good method. It won't be subgame perfect, but you could just say, do the best planning I can with a limited set of information if you don't want to have this problem grow in size. But you just do that step, it gets you your next hypothesis non-negative, and repeat. So is this method good? Right, we so far have just argued this thing has a good inductive property. It's greedy in how it moves forward. It's going to attain our higher standard of subgame perfect. To articulate that, I want to think about, at any iteration n, I could get lazy and say I've moved this inductive hypothesis hn forward to now. I'm tired of solving my subproblems. Let's just run OGM till the end. OGM was the best not thinking way to carry this induction forward. So I could, at some iteration tau n, just start doing OGM. I'll get new taus, tau hat, that are what I would get if I just ran the older method all the way out to the end. And they have a nice recursive form, so I can come up with them. They just do this momentum style updating. So if we do that, we can then write a nice theorem. So this subgame perfect method is subgame perfect, meaning that for any iteration little n that we're at, I can guarantee that the final gap I get to, the final performance ratio, will be less than the final tau I reach, which will be less than if I got lazy and just ran OGM till the end, which is exactly what the Minimax optimal strategy would be in this subgame. Okay, so the proof of this, okay, I kind of fit it on a slide, but I've omitted, admittedly, all the gory details. The first two inequalities are in a sense by definition. The first one is just the inductive hypothesis we built. The second one, kind of, we use just a smarter, greedier update than OGM. We're going to come out ahead of it. The last equality is the interesting one. That says that we exactly know the Minimax optimal strategy on any subgame. So this number 1 over tau hat is definitely an upper bound on the best any algorithm could do on the remaining game, because OGM generated it. If I ran OGM, I would have gotten tau hat, and that's one method. So the minimum overall methods is smaller than that. You can use weak duality to flip the order of the min and the max. That'll be a lower bound. And then, okay, the last technical bit that you'll have to see the paper for, we can construct a particular function that agrees with the past data so that no gradient span method can do better than 1 over tau n. So we can make a strategy for Bob that would show and you can't do better. At which point we've now wedged all of this stuff here between 1 over tau hat. So it's actually equalities all the way through. So we get our equality for the theorem. that tells us that this way of finishing out the game is the minimax optimal strategy. You get a nice min-max theorem, and mathematically that makes me happy, that at each of these subgames, you have this kind of classic min-max structure. Okay, to see the actual constructions for like this hard problem, I'll leave you to the paper, but you can get this hard problem in essence, kind of in line with your question before. If we know that our algorithm is going to be optimal, you should have this kind of complementary slackness that every inequality the algorithm used should be met with equality in the hard instance. That'll give you a bunch of constraints on what that instance could be. They end up effectively uniquely defining the worst instance. So some complementary slackness ideas would give you how to construct that.
Just one quick question.
Yeah.
If I go, you said we could, instead of doing all those steps or whatever, we can just do 10.
Yeah, instead of keeping all the memory. Yeah.
If I do just one, am I guaranteed that'll be better than doing OGM?
It'll be identical. If you only know your current state, if one means your current state and one memory ago, then you'll be better than OGM.
I see.
And your planning problem will be some like 2x2 problem that presumably has a closed form.
So
every little bit helps. And we're going to see it doesn't take much memory to get almost all the benefit. So, okay, I'm not really one for like computing. Yeah. So yeah, there's something I swept under the rug here that to build this hard instance, I'm doing something, I'm cheating. So thank you for your question. Shame on me. This theorem requires you to be thinking about problems of generic dimension. So if you're thinking about optimizing problems of any dimension, in particular problems of dimension higher than the number of iterations you did, this hard problem instance that gives me the last inequality has dimension n+1. So the problem instance that does the last step is one of high dimension. Otherwise, to the earlier question, your algorithm could just solve exactly if you found the whole space. So to build this hard instance, I had to go to higher dimension. So implicitly, it's under the hood here that I'm saying you're subgame perfect against an opponent Bob that can play in any dimension. Rather than for a static dimension, eventually a gradient span method should be perfect.
Question?
Yeah.
So for the optimization problem that you solve to sort of find the new parameters, is it you're keeping the hypothesis no potential non-negative, but you're doing that sort of. There could be choices for mu at lambda that are not that are negative, but keep the hypothesis non-negative. No.
Yes, but they wouldn't give me a legit proof. So
okay, so you need
right, because the way that I'm saying the hypothesis is non-negative, yeah, you could hope that maybe there are proofs like that. At least the argument would then have to be different from this. I couldn't just say it's a sum of non-negative stuff, so it's non-negative. I need to have some independent creative proof. There's some in this family of literature called performance estimation. I can guarantee you that won't happen. That every proof could be written of the form adding together these co-coercivities. That's a weird, deep result that I find unintuitive. But in fact, this proof technique is sufficiently strong to prove anything you could want. So if you had a clever proof that got around this, I'd be able to rewrite your clever proof back like this. Okay, so I want to see how good this is actually doing. So my proxy for that is, while I'm running a method on an actual instance, I just drew some random instances. I'm not really big in like heavy computing. I'm a theory guy. I'm going to draw random instances, and at iteration little n, I'm going to see what's my guarantee at the end that I'll do at least as good as if OGM ran forward. I can just go come up with tau hat capital N. It's what OGM would guarantee me if I run out to the end. These will always be at least as good as if I ran OGM the whole time, but they should get better whenever Bob makes a mistake. I should be able to ratchet up tau and grow faster and get an increasingly good guarantee. So we have these guarantees tau hat along the way that are saying what's the quality of guarantee I'm guaranteed to get by the end of the method. And I can watch while I solve an instance and see how much my guarantee improves. So if I just ran OGM, that's the blue line here, for a least squares problem with random data, OGM is saying you'll get something about 10 to the minus 4 as the quality guarantee after running 300 steps. If instead you ran our subgame perfect method, you see that while it runs, Bob makes mistakes. He's not doing the worst possible instance. He's doing this least squares instance. And we repeat until eventually finishing, say, something like 10 to the minus 8. So we can say that concretely doing this adaptation would have got us about 3 orders of magnitude better, maybe 4. If I run the method with just a memory of 10, just remember the last 10 iterations, then we see it's quite a bit better, very similar to the full memory method, but now just tracking 10 gradients and solving subproblems of size 10. We get almost all the gain from a limited memory setup. Of course, my subgame perfect theorem is only about the dark green line. If I add regularization, okay, here I just run 30 iterates. The optimal method is only guaranteed like 10 to the minus 3. This is a little bit cherry picked. I chose the plot that looks best, but across lots of random instances, we get quite a bit of gain. When you look at an actual problem, our subgame perfect method gets to exploit the particular functions and gradients seen and build a much better certificate than you would have if you were a priori worried about the worst case. Yeah.
So I guess, let's say, given a real function, all these stuffs given from the Bob are basically all these mistakes.
Mm-hmm.
And then now what you're suggesting is basically assuming that all these given mistakes, I'm trying to do the best action, assuming that it will do the future optimal actions from there,
right?
Right.
So, at every step, I'm worried that Bob is about to get smart.
Yes.
He's given me these least
Yes.
squares answers so far, but the
Yes.
algorithm doesn't know he's going to keep answering least squares.
Yes.
Yeah.
But in practice, I guess that's not going to happen. It will keep making the same mistakes forever. So can you go more aggressive? That's what I'm wondering.
You can't go more aggressive in like this minimax optimal sense. If you're worried that you're thinking about the set of all smooth convex functions, this is exactly as aggressive as you can be.
True. If you
right.
assume
So
that,
if you had some extra structure, if you want to stay within this subgame perfect game theory lens, one sense is that you're saying that the worst case functions are these like piecewise quadratic weird things, and you want to shave those out of the problem class somehow and look at a more restricted class of.
Or in other words, can we make some assumption on like the level of Bob's mistakes? Let's say
I don't know how to make it theoretically analyzable, but that'd be an interesting kind of direction to say that Bob has revealed that he's a low caliber player, and I should only be worried about low caliber moves in the future. I don't know how to convey that mathematically. That'd be very neat. I don't know if any like chess engines online do that. If the chess engine figures out you're bad at chess, does it start making mistakes to beat you quicker? I don't know. Okay, so I did a little bit more numerics. I took every smooth convex problem I could think of. So least squares with regularization, with a Huber regularization, with the sum of Hubers on components, log some x, the Moreau envelope of the max function, just stuff that's smooth and convex I could code up. I generated 7 random instances from each type. So I had a bag of 49 instances, and I did the thing that I see in good computational papers, where I gave a performance profile. I ran all the methods, asking for 10 to the minus 6 or 10 to the minus 9 accuracy, and I logged at each iteration how many of them had hit the target yet. So a curve up and left is a very good method. And BFGS is a very, very good method. That's quasi-Newton stuff. It's really effective. So that's in red, and the limited memory version is in pink. And it quickly solves almost all the problems I set up, and then just has to work a little bit on the last few. If you run our subgame perfect method or its limited memory version, it's really comparable at getting 6 digits of accuracy, a little bit weaker for getting 9 digits. And then for reference, I included gradient descent. My example problems were too strongly convex, so gradient descent did really good on some of the problems, and then couldn't solve the last 30% at all. That's a problem with my bag of problems, but gradient descent, flat lines, OGM, this optimal method, is just rather abysmal. At getting 9 digits, it never gets there because it's too pessimistic. So it just plots along. And if I use real problem data instead of randomly generated data, you get rather similar looking curves. Okay, I have fewer problems in this bag because I just have less real data. Yeah. I see. Yeah, so this blue one here is OGM. It's the Minimax Optimal method that is just not adapting to what's being seen and just always scared about the worst case function. And gray here is just gradient descent, no intelligence, but it happens to be very good if the problem is strongly convex. So it solves a fraction of them quickly. Okay, so
Can you just comment a little bit about BFGS and LBFGS? So
yeah, so
why they should be working better? Is it because they're breaking this assumption that gradient span?
BFGS follows the gradient span assumption. So when I was inventing this theory, I was really optimistic we were going to beat BFGS, and I was hoping to go on a talk tour and tell people I have something better than BFGS. I don't have something better than BFGS yet. BFGS is a gradient span method, but it's using other structure. So it's getting to adapt if my estimate of L was too pessimistic, or if near optimal, the problem is more smooth. Our method has no way to take advantage of that because it just has a static L hard-coded from the start. BFGS gets to adapt. So sometime in the next 6 months, I'll get a paper out doing an adaptive version of this. My numerics doing an adaptive version were as good or better than BFGS. So if I let the algorithm figure out the right L and then run with that, it makes up the gap. But yeah, maybe from the...
My other question.
Yeah. You have to do a fair bit of legwork, not a terrible amount, but a fair bit of legwork to get it to be adaptive. You just can't directly backtracking line search or something, but it's doable, coming soon. Okay, are there any more questions on this? I've similarly to last time I gave this talk, not left a terribly large amount of time for gradient descent. So I'd love any more questions with this while this is top of mind. And then I'll give you a vignette of how to do gradient descent. Okay, on to a new fun thing. So I want to run gradient descent as well as possible. This is putting handcuffs on us. All the previous methods were able to know the past gradients. They were able to do momentum updates and kind of build some aggregate knowledge of how to optimize this problem. Gradient descent ties our hands. It says at each iteration, you're at xk, you get to see the gradient, you move some amount in the negative gradient direction, no room to go back in the past or use other knowledge. So these are weaker algorithms, but I'd like to run them and choose the step sizes, hk, as well as possible. The step sizes are the only lever I have to control in algorithm design, so we're just going to choose a vector of length n to describe our n steps. And so just as a shorthand for these slides, if you have an L smooth problem with distance d to optimal, I'll call that FLD. At some later moment, there's no way I'm going to get to it. Sometimes you might want to put bounded objective gap instead of bounded distance to optimal. But those are the problem classes we're looking at. And so the kind of classic theory, what I pointed to earlier was that if you run gradient descent with a constant step size h equal 1, I baked in the divided by L, you can get a rate that looks roughly like 1 over 2n. The reason for that, I'm sure many of you have seen that or taught a class doing this. You point to the descent lemma. You say, I can draw these quadratic upper bounds. A step size of size 1 is moving to the bottom of the quadratic upper bound. That's kind of the greedy best one step. And you do that repeatedly. And if you want to come up with a proof of that rate, it's effectively just use the descent lemma repeatedly, draw these upper bounds, and go to their minimums. There's theory that's been developed recently that gives exact characterizations. So if you want the exact worst case for some step size between 0 and 1, we know exactly what the worst case is. If you wanted to minimize gradient norm, we have an exact description of the worst case. And the worst case for all of these occurs on a Huber function. Gradient descent with a small step size is going to really struggle when the problem is a long, slow walk down. So we don't need complicated worst cases. I can understand the worst case for those just by saying the function's very flat and optimal's very far. Gradient descent doesn't have a good way to cover that distance because there's no momentum, there's no kick to get you across it faster. So it was conjectured and then recently proven that if you wanted the best constant step size, not limited to be less than 1, what you should do is choose the step size h solving this equation. That equation is just saying that on a Huber function, you do as bad as on a quadratic function. If you go and balance those two worst cases, you get that pink equation that tells you the best step size h over all constant step sizes. That makes some intuitive sense. That's saying that on the flattest possible function or the curviest possible function, you have balanced your worst case. So to me, that's a sensible design standard, not as principled as the subgame perfect style of thinking, but I should expect that my methods are balancing very flat functions and very curvy functions. So that's going to be the key definition that's going to carry us forward to do even better design. I'm going to say that a step size schedule, maybe not constant, is F composable. Eventually, we're going to compose these things together. Admittedly, the name right now looks weird. It's F composable with rate eta if the worst case is convergence at rate eta and the rate is attained on a quadratic and a cuber. So you're F composable if you have a rate and it successfully equally balances these two extremes. So the design problem, I'd like to come up with the step sizes H that minimize the worst case. That's what would be the best gradient descent schedule in a minimax optimal sense. Solving that min-max problem is super, super hard. So in several people's master's and PhD theses, they analyze this for a small number of steps. N less than 3, they're able to exhaustively figure out that min-max problem. Shubho Dasgupta and Ernest Ryu came up with this branch and bound approach you can use on that problem, solved it numerically up to about 50, and you get these weird schedules. The best one step numerically is 1.49999. Okay, that's 3 halves. 3 steps, it tells you you should do something that looks like root 2, 1 plus root 2, 3 halves. That's the best 3-step method according to the MIT supercomputer. I can't play this guessing game very long after that. I stared at their paper. This paper is what originally got me to care about this gradient descent design problem. Yeah.
So are these like slight errors actually part of it, or are they just?
No, that's just that you just did a branch and bound method. I mean, you just solved to some accuracy, partitioning up the space, and
so it's just an accuracy thing, not inherent.
Right. This is just that's what the supercomputer spat out, and you should trust it as much as any computer. There's not much. Morally, we shouldn't trust computers that much. I don't know if that's something I need to say. They do stuff like this. 3 halves is the right answer. Okay, so when you go look at these, you say, what were the optimal 10 steps? They wiggle around in a way that's not so beautiful. But they sometimes are very large. Out of the optimal 50 steps, the supercomputer said to take a step of size like 38. So that's weird. I really wanted to resolve this. That was my original motivation to look at this. Jason and Pablo gave a beautiful answer for this. They said if you look at these silver step sizes, you can get something like that to happen. These are schedules where you're going to build the next schedule, pi k plus 1, by doing the previous schedule, some number beta, which grows exponentially, and then the previous schedule again. These look fractally. So when you do this construction, you take the previous schedule, you put it on the left and right, and put a bigger number in between. And you put it on the left and right, and a bigger number in between. Repeat it all the way out. That gives you a proposed step size schedule. They call these silver step sizes. And they proved gradient descent with these step sizes will converge at a rate that looks like 1 over n to the log base 2 of 1 plus root 2, which is like 1.27. Rather magical. This theorem is almost tight. The thing in their paper is off by a factor of 2. If you use the theory that I might have time to tell you about, you get a factor of 2 on this, and that becomes an equality. But these step sizes are beautiful, just like visually. I love that fractal. But they're not quite perfect. I mean, one critique is that we looked at the supercomputer once, and they're not beautiful. What Jason and Pablo have is beautiful. So what Jason and Pablo have isn't right, because it's not what the supercomputer found. Yeah.
So can you go back, because in any so it appears the fractal.
It's fractal-y.
Yeah.
It's fractal-like, but it's not a perfect symmetric beauty. It wibbles about. So these silver step sizes are not F composable. They don't have this property that I said good algorithms should have. They don't equally balance Huber and quadratic. Instead, they're balancing a different quantity.
So that's because we put as a benchmark the Huber and the quadratic. I thought that we like that because we know that it's a lower bound. But
so
maybe...
I'm saying morally, I think a good algorithm should balance those two. That's my moral position, right? It's not coming from math.
Okay.
I'm saying this is the flattest function, the curvest function, and I should be worried if those aren't equally balanced.
Okay.
Then you have the opportunity to be more aggressive or less aggressive.
I'm just saying that maybe there is another function that makes it worse.
It's possible it exists. I'm going to recover what the supercomputer found. Okay. So this is on a path towards getting something at least as good as a supercomputer up to 50.
Supercomputer is solving the Cooper and the quadratic.
No, the supercomputer is solving this general problem.
Okay.
It's finding the best step sizes over all problem instances. So the supercomputer has the truth up to numerical error, and I want to match the supercomputer. But I want to do it mathematically so that there's no computer error. Okay. If you dig into the proof for these silver step sizes, you'll find that they're balancing a different inequality. And this is a weird inequality you just discover by going through the proof with a fine-tooth comb. They're balancing this S-composable inequality, which is some way of balancing the final gradient size, the final distance to optimal, and the final objective gap as being less than the initial distance. They get some rate that shrinks with a value of eta going to 0, and Huber and quadratic are tight on that inequality. So my claim is that what the silver step sizes have balanced is that they are a perfect method if that's how you wanted to measure convergence. If you wanted your convergence rate to be that you drive those three quantities to 0 in that weighted fashion, silver does it perfectly, and on the flattest and curviest functions, it's equally bad. So we'll call that S-composable. If you have that inequality, you can pull out an objective gap and a gradient norm convergence rate separately. So the silver step sizes are going to be good, not just at minimizing the objective gap, but minimizing the final gradient. So they're doing more than we asked, which means they're a little bit wasteful. If we wanted the best method for objective gap, I shouldn't waste any time getting a good gradient size. I should just focus on the one objective. So how are we going to do better? I named these things S-composable and F-composable. We're going to compose them. If you have two schedules A and B with this S-composable property, I'm going to bow tie them together. A bow tie B is a bigger schedule where you do A, some big step in the middle, followed by B. What should the big step in the middle be? Well, I would like this to balance that inequality on Huber and quadratic. If I say that this step size should have the same performance on Huber and quadratic, that gives me an equation. That equation knocks out my one unknown of what to do in the middle. And so you get this weird formula. But what goes in the middle is whatever it would take to keep Huber and quadratic balanced on the S-composable inequality. And you'll get some rate that comes out with it. And okay, a theorem, if you started with S-composability and you bow tie them together, you still have S-composability. So you can build the silver step sizes out of bow tying stuff together like this. You can do the same thing with this F-composable property. If you have a sequence A and B, you can join them with a different choice. The choice there is whatever gets Huber and quadratic to be equally bad at objective gap. Instead of balancing the weird S inequality, if you balance objective gap, it tells you what to put in the middle. We have a way we can join those, and I denote it with a right arrow for how to join A and B. And a theorem, if you have A being S composable and B being F composable, when you right arrow them, you get F composable. So we have some rules on how you can combine things. You can combine S and S and get a new S. You can combine S and F and get a new F. We now have these rules, and we can build things and get proofs for long sequences. If we just run through these, you get some weird constructions. The empty sequence vacuously satisfies all of our definitions. So you could bow tie empty and empty together, and you'll get root 2. As the empty something empty, root 2 is what goes in the middle of the balance. You could bow tie those together, and you just get more and more sequences. The silver step sizes are what you get if you just recursively bow tie together. Empty and empty gives you root 2. That's the start of silver. If you bow tie together root 2 and root 2, you get root 2, 2, root 2. That's the next silver sequence. So this bow tying operation generates that beautiful fractal before. If you just recursively apply it, you get these S rates that come down here, and those fix the factor of 2 issue I pointed out in their theorem. You get a factor of 2 better by using this bow tie operation. You can do the same stuff with F composable. You can arrow and bow tie stuff together to build bigger and bigger sequences. And you can get things that match the supercomputer. So if I go look for patterns that match the first 10 things the supercomputer found, I find that if you algebraically combine in these weird ways, you get what the supercomputer found. I mean, up to like numerical error. But okay, this tells me that, oh, there's there's some magic here. All you need is empty step sizes and these two operations, and I can recover everything the supercomputer found. Okay, we recover what the supercomputer found up to about 25, and then we start doing better than the supercomputer, so its branch and bound was not getting the accuracy tight enough. So these match everything the supercomputer had until we start beating the supercomputer, and then we just have better schedules. So, okay, I'm pretty happy with these. This tells me where did those weird things from the computer come from. They came from iterative composition, balancing the silver inequality and this F inequality.
You discover the composition by taking everything, or like, let's forget the first step. Let's go to the 0.04020, that it is a very specific combination, and I'm asking that combination, you discover it by trials,
right? So,
or there was proof how you should combine.
So I came up with the ones that matched the supercomputer by just brute force trying every combination.
Okay.
But you shouldn't do that, right? Okay. Next slide.
Okay.
So what you should do is you should dynamic program over these operations. It ends up that these have really nice monotonicity properties. So in effectively linear time, I can tell you the best schedule of any length. If you want 1,000,000 steps, it'll take me about 1,000,000 flops to dynamic program and tell you the best way to join things together to get step sizes that just combine empty sequences by these operations. So we can do as well as possible out of these operations and get a guarantee that says, you get some very optimized numbers I didn't write formulas for. You get a guarantee on the objective gap being small. Since all these things are attained on Huber and quadratic, I know there exists an F that these things are nearly tight. If you just go, we built in that we'd have tight problem instances. So I always know lower bounds, that my theory couldn't be improved too much asymptotically. But okay, in particular, what I believe is that all the optimal step size schedules are basic. That means that they can be built out of our operations and F composable. If it's true that the optimal method is basic and F composable, then this dynamic programming gives the minimax optimal steps. I don't know how to prove that the optimal step sizes have those properties, but the supercomputer tells me they do. Makes me happy. Okay, that's maybe the best way I can build step sizes. So thank you all for your attention.
Could you share some quick, do you have any intuition about like why this kind of non-monotonic, symmetric or weird looking step sizes are optimal? It makes sense.
Yeah, I think the minimax sense is particularly hard. So one thing I can't do that I would really like is to be able to give lower bound. I don't know how to say, here's an instance that's very hard, and any gradient descent method to do poorly. Because I think that would be the way to really meaningfully answer that question, is to say, here is my very hard instance, and look, to do well on that instance, you needed these long fractally steps because of something in its nature. But I don't know how to come up with a hard instance doing the max min problem that would say why you need these. Because to say you need them would really come from an instance that necessitates them. I don't know how to do that.
Okay, thank you.
Oh, thank you.
It's really interesting that